double integrals. Let f be a continuous function of two variables. Define on a rectangular domain D. The double integral of f, the double integral of f over D is symbol of double integral on D f x y d a. D is xy, so a is smaller than x and is smaller than b. C is smaller than y, is smaller than d. A, B, C, D is a constant, are constants. We can draw easily x, y, a, b, c, d. Rectangular domain. dA is this area. dA represents a differential element of area A. How can we evaluate this double integral? The question is answered by the following theorem. Theorem 22. This is Fubini's theorem. If f is continuous on a rectangular domain D, then double integral on D f x y dA is equal to a b c d f x y dy dx, or is equal to c d a b f x y, first is dx and dy. Fubini's theorem tells us how to compute a double integral by means of iterated integrals. It also states that it doesn't matter which variable we integrated with respect to first. We will get the same answer regardless of the order of integration. If fxy gx product hy, and we are integrating over the rectangular domain D. Then double integral on D fxy dA is equal to G product H dA is equal to, from A to B, gx dx product from C to D, hy dy. How can you state this fact with your own words? Answer: if we can break up the function into a function only of x times a function of y, then we can do the two integrals individually and multiply them together. Example: compute the double integral on d x exponential xy dA, where d is a region given by -1 is equal smaller than x is equal smaller than 2, and 0 is equal smaller than y is equal smaller than 1. While we can technically integrate it with respect to either variable first. In this case, it will be significantly easier to integrate with respect to y. First, as we will see, double integral on d x exponential xy dA is equal to -1 to 2 from 0 to 1 x exponential xy dy and dx. This boundary is for x, this boundary is for y. And firstly, we calculate this integral. We want to integrate respect to y. X like as constant. So is equal to -1 from -1 to 2 and x 1 divided x exponential xy 0 from 0 to 1 and dx. Calculate easily. -1 to 2 and goes these terms, and firstly we write 1 and then 0 exponential x minus exponential 0 dx. This is 1. So from -1 to 2 exponential x minus 1 dx. You can integrate it, this term, easily. Exponential x minus x from -1 to 2 and exponential 2 minus 2 minus exponential -1 plus 1. So exponential 2 minus exponential -1 minus 3. This is solution. Another example. Evaluate double integrated on d x product cos square y dA, where d is xy. So -2 is equal smaller than x is equal smaller than 3, and 0 is equal smaller than y is equal smaller than p divided 2. Since the integrand is a function of x times a function of y, we can use the above given rule. So we can easily from -2 to 3 boundary of x dx, and from 0 to p divided 2 cos square y dy, and you calculate easily this term. 1 divided 2 x square from -2 to 3, and this term, you remember, cos square y is equal to 1 plus cos 2y divided 2. So from 0 to p divided 2, 1 divided 2, 1 plus cos 2y dy. This area is calculated easily. 5 divided 2, and this is calculate 1 divided 2 y plus 1 divided 2 cos sin 2y from 0 to p divided 2. This is solution is 5p divided 8. Now double integrals over non-rectangular regions. Non-rectangular regions. we want to define and compute double integrals over regions more general than rectangles. More specifically, we want to extend the concept of the iterated integrals to general regions, subject to the following conditions. A plane region D is said to be vertically simple. If it lies between the graphs of two continuous functions of x. That is, D is equal to xy, so A is equal smaller than x is equal smaller than b, and g1 function of x is smaller than y and is equal smaller than g2 function. These are function of x. The numbers a and b, respectively, the smallest and the largest values of the x coordinate of points in D, where g and g1 and g2 are continuous on AB. Some examples of vertically simple region show in the following figures. For example, x, y, a, b. This is g1 function and g2 function. Array is this. So, another example, x, y, a, and b. Y is g1x and y is g2x. Array is this array. Another example, x, y, a, b, y is g1x and y is g2x. Arrays this. D region. If D is vertically simple, then it is bounded from below by the graph g1x and from above by the graph g2x. Bounded from below by g1 and from above by the graph g2. Bounded from below by the graph g1 and from above by the graph g2. Say, bounded from below by the graph g1 and from above by the graph g2. Not that. Not that. For a vertically y simple region, any line parallel to the y-axis intersects D along at most one straight line segment. If all vertical arrows lie in the region of integration D, then D is called y simple region. This is y simple region. A horizontally simple region is one that lies between two functions of y. Two functions of y. That is, D is equal to xy. So C is equal smaller than y is equal smaller than D, and h1 function of y is equal smaller than x is equal smaller than h2. h2 is a function of y, where h1y and h2y are continuous on CD. The region in the following figures are horizontally simple. For example, area x, y, c, and d h1 function and hy function. This area is d, or x, y, c, d, h2y function and h1y function. Area is d. Sometimes instead of the term horizontally simple region, we use the term x simple region. X simple region. And the term of y simple region instead of the term of vertically simple region. The following theorem tells us that a double integral over a y simple or x simple region can be found by evaluating an iterated integral. Theorem 23. Fubini's theorem for general region. For general region. Let f be a continuous on a region D. 1. If D is a Y simple region, then double integrated on D f x y dA is equal to from A to B, from G1 to G2, fx y dy dx. 2. If D is a x simple region, then dfx y dA is equal to from C to D h1 y and h2 fx y dx dy. We think about non-simple region D. This is non-simple region. The non-simple region D is the union of the y-simple region D1 and x-simple region D2. Divided this line D1 and D2 and h1y h2y g1x and g2x. In other words, the region D can be split into two separate simple regions D1 and D2. So, if you want to calculate double integral on D, fx y dA is equal to from A B g1x g2x fx y dy dx plus cd h1y h2y fx y dx dy. Example. X y 0 0 1 0 1 1. This is y is equal to x area this. This is D region. Evaluate double integral on d xy dA. The region is both x simple and y simple. First, we make a sketch of the region D. We see that D can be viewed as a y simple region. That is, D is x, y, so 0 is equal smaller than x is equal smaller than 1, and 0 is equal smaller than y and is equal smaller than x. Observe that if we integrate over a y simple region, we integrate with respect to y first. The appropriate limits of integration can be found by drawing a vertical arrow. This arrow. The arrow begins at the lower boundary, y is equal to 0, and terminates at the upper boundary, y is equal to x. Using Fubini's theorem for general regions, we obtain double integral on d xy dA is equal to from 0 to 1 and from 0 to x, xy dy and dx. And first we calculate this integral. So from 0 to 1 x y square divided 2 from 0 to x dx. So is equal to 0 to 1 divided 2 x square minus 0 dx is equal to 1 divided 2 from 0 to 1 x cubed dx. So x fourth divided 8 from 0 to 1 is equal to 1 divided 8. This is solution. And alternative solution. We can view the region D as an x-simple region. D is this times x, y, so 0 is smaller than y is equal smaller than 1, and y is equal smaller than x and is equal smaller than 1. Y this time this arrow, y is 0 and 1. Lower boundary is y, upper boundary is 1. If we integrated over an x-simple region, we integrated with respect to x, a horizontal arrow starting from the left boundary of D described x is equal to y, and terminating at the right boundary of D described x is equal to 1 gives the lower and upper limits of integration with respect to x. Once again, using Fubini's theorem, we obtain double integral on d x y dA is equal to from 0 to 1 and from y to 1 xy dx dy. So from 0 to 1, calculate easily x squared divided 2y, y and 1 dy. So is equal to from 0 to 1, we write on there 1 square minus y square divided 2y dy, and calculate easily. You know this integral, y squared divided 4 minus y4 divided 8 from 0 to 1. Calculate 1 divided 8. Same answer. We obtain the same answers regardless of the order of integration.